Thanks very much. Thanks to the organizers for the invitation and for the very nice conference. So it says in the title of the conference, part of the topic is nilpotent structures in combinatorics. So here we have graphs which are combinatorial and nilpotent groups which are fairly cleanly nilpotent. So I hope this falls squarely in that aspect of the topic. This is, I'm going to talk about an ongoing project that I have with Romain Tessera in Paris. And I'm going to start, so although I'm going to try and make the focus for most of the talk, the nilpotent stuff, given the topic of the conference, I'm going to start by describing one of these applications to probability, or at least motivating things in that way, because that's what motivated me, got me interested in this project in the first place. So I'm going to talk about a very classical, I want to say one more thing. Although the title says vertex-transitive graphs, you're not going to hear me mention vertex-transitive graphs again until right at the end. I'm going to do everything in the special setting of Cayley graphs, just because that makes the exposition a bit clearer. So hopefully I'll have time at the end to say a bit about generalizing to vertex-transitive, but if I don't have time, let me just tell you now that everything I say can be generalized in a suitable way to transitive graphs as well. Right, so there's a classical probabilistic notion that I want just to describe very quickly, which is the notion of a random walk on a graph. So I've drawn there the standard Cayley graph of z squared. But actually what I'm about to do makes sense on any graph. You can define what's called the random walk by it's a process which starts at some vertex of the graph. For us, this will always be the identity, although it doesn't really matter. And then at each stage of the random walk, the walker is at a given vertex. The walker looks at all the neighboring vertex, picks one uniformly at random, and moves to that vertex. So let's say, with probability 1/4, the walker will move here. And then with probably 1/4, they'll move there, and then maybe here, walk around. At random, they might go back on themselves. And various things can happen, but what I want to particularly emphasize is one of two possibilities. Either the walker eventually finds their way back to the starting point, or maybe, depending on the graph, maybe the walker will wander off to infinity, never to return. So I'm going to call this, if the walker goes off to infinity without returning to the starting point, I'm going to call that escaping to infinity. And a graph is called recurrent if the probability of escaping to infinity is 0. And transient otherwise. Okay, so it's transient if there is some positive probability of the walker disappearing off to infinity without first returning to the starting point. Now it's known that this Cayley graph z squared is actually recurrent. So the walker is guaranteed to find their way back to the starting point eventually. But if you draw the same thing but in 3 dimensions, z cubed is known to be transient. So there is some positive probability of never returning to the starting point. Veropoulos in the mid-80s gave a complete characterization of those Cayley graphs for which the random walk is a recurrence. And he showed that a Cayley graph is recurrent if and only if the group on which the graph is defined is, well, if it's finite, that's a kind of trivial case, or virtually Z or Z squared. And here throughout the talk, I'm going to use virtually to mean up to finite index. So virtually Z means has a finite index subgroup isomorphic to Z. Virtually Z squared means has a finite index subgroup isomorphic to Z squared. So in a sense, this example here, an even easier example of just an infinite line graph, capture essentially all the examples of recurrent Cayley graphs. Now, let me tell you a tiny little bit about the proof of this. I'm not going to go into much detail, but I want to give you a hint at where the Nilpotent groups come in. It's actually a little bit easier to see that if we restate this question or restate this theorem in terms of something called growth. So let G be a group and S a finite generating set. And I'm just going to make a couple of assumptions on S for notational convenience. This doesn't really make any real difference, but I'm going to assume firstly that S contains the identity, and secondly that S is symmetric, so it contains inverses. Every element of S, its inverse is also an S. And that's just so that I can write the ball, so S to the n, by which I just mean the set of all n-fold products of elements of S. Is exactly the ball of radius n, so the identity in the Cayley graph. And very roughly and generally by the growth of the group, I'll put with respect to S in brackets, because we'll see soon that it doesn't really matter which S you choose. The growth of G refers to the growth of the size of S to the n, so the number of elements in the ball of radius n in the Cayley graph, as n goes to infinity. So that's just a kind of vague notion of what growth means. We have some more precise definitions. I'm about to make one of them. But in particular, we say G as polynomial growth. So this is just a vague notion of what we mean by growth. This is a concrete definition. G has polynomial growth if there exists positive C and D such that S to the n is bounded by C and to the D. Well, all in. Okay, so if the balls of radius n are bounded by some polynomial. And let me just tell you some quick facts about polynomial growth. I'm not going to prove these. I'll give you some hint about how to prove them in a second. I'm just going to write down some standard facts. So the first fact is that polynomial growth. Well, firstly, I won't write this down, but it doesn't depend on the choice of S. So if you have this bound for some S, you have such a bound for any other choice of S. That's a very easy exercise. A slightly less trivial fact is that polynomial growth implies that there exists C and C positive and D a non-negative integer, such that these balls are not just bounded above by a polynomial degree D, they're also bounded below by a polynomial degree D. So C n to the D is at most S to the n is at most big C n to the D, or n. And a particularly important point to note here is that D has to be an integer. So you can't have growth of like n to the 1.5 or something. That can't happen. It's always the degree of polynomial growth is always an integer. Another fact is this D doesn't depend on S. And then another fact which is particularly relevant to this theorem of Veropoulos is that D is at most 2 if and only if G is finite or virtually Z or Z squared. Okay, so I've just asked you to take those statements on faith for now if they're not familiar to you. And so I can now restate Veropoulos' theorem is equivalent, therefore, to saying that G is recurrent if and only if G has at most quadratic growth. And in fact, what Veropoulos actually proved was that G is recurrent if and only if size of S to the n is at most big O of n squared log n. But because you can't have anything between quadratic and cubic, this is exactly the same as what I wrote here. Okay, so this is what he actually proved. And then using these standard facts, he deduced the version that I stated up here. Now, this is where the Nilpotent group comes in. These facts are actually corollaries of a famous theorem due to Gromov. The facts above will follow from the following theorem. Due to Gromov, and that was in the early 80s. And he showed that polynomial growth implies virtually nilpotent. So if you have a group of polynomial growth, it has a nilpotent subgroup of finite index. The converse is a fairly easy exercise. Okay, so I'm not going to go into detail about how you deduce these facts here from Gromov theorem, but I'm not aware of any other way of proving any of these. And it's somehow this is the deep part. So these are not trivial consequences of Gromov's theorem, but they're reasonably routine, whereas Gromov's theorem is quite hard. Yeah. Yeah. Right. Yeah. Exactly. So in fact, so this is somehow the first. This is the statement that the first reading of his proof gives the statement. But in fact, we know this is true if and only if it's big O of n squared because of these. Right, yeah, exactly, yeah. So if you have polynomial growth, you know it's asymptotically bounded above and below by a polynomial of integer degree. Yeah, you're welcome. Right. So that's all well and good. Now, what Roman and I have been looking at, or one of many things we've been looking at, is some more finite tree versions of this theorem of Veropoulos. So in particular, this motivated by a conjecture of Benjamini and Cosma from about 20 years ago. For the sake of time, I won't state the conjecture now. I'll state some general motivation, state our theorem, and then just tell you which bit of the theorem verifies their conjecture. For the general motivation, let's consider now, rather than an infinite Cayley graph, I want to consider a finite one. I'm going to consider Z mod NZ cubed. So you can think of that as being with n potentially quite large, but finite. And you can just think of that as a big cube. We've got to identify opposite faces or whatever. But somehow, rather than infinite 3 space, it looks like this. And we've got the origin in the middle there, the identity in the middle. And now imagine you run a random walk on this group. The random walk walks around, and until the random walk gets to distance roughly n from the identity, it has no idea that it's in a finite group. So somehow, if you look at a ball of radius n around here, just from knowing that Z cubed is recurrent, is transient, sorry, you know that you have some positive probability that this random walk will escape from this ball of radius n. Now, once it gets much beyond that distance, then it starts to, it reaches the edge of where it can get to. And of course, eventually, because the group's finite, it will find its way back. But somehow on scales up to roughly the diameter of the graph, the random walk doesn't see that. And in fact, it's not hard to show that. Let's see if I write P, I'm going to write. So I said escaping to infinity was the event that the random walk goes off to infinity without returning to its starting point. I'm going to write escaping to distance n to mean the event that the random walk gets to a distance n without first returning to its starting point. And just because this graph locally looks like Z cubed, we know that there is some non-trivial probability that this happens. And Benjamini and Cosma, about 20 years ago, conjectured that this phenomenon should hold much more generally, not just for graphs that are explicitly assumed to be essentially locally isomorphic to Z cubed, but just by knowing the size, just by knowing that the ball of radius n has cubic size should be enough to tell you that there's some lower bound on the probability that the random walk escapes to distance n. So I'm going to write that down precisely. Or write down something even more precise, actually, which we proved. I should say when, 2020, I think. So we proved the following. There exist universal constants, big C and little c, such that in an arbitrary Cayley graph, I'm going to bound the probability of escaping to distance n from above and below. The lower bound will imply, in particular, imply Veropolis' theorem. And it's C times the minimum of 1, and we have size of S to the n over n squared log n size of S. And on the right-hand side, we just have C size of S to the n over n squared. And both these bounds are sharp. And the lower bound implies, in fact, strengthens and generalizes a conjecture of Benjaminian Cosma of 2002, I think. So let me just, I'll go into a little bit of detail. I want just to point out that this n squared log n, you should think of as being the same n squared log n that appeared here. And I didn't tell you this, but this probability of escaping to n, as you let n tend to infinity, that really does converge to the probability of escaping to infinity. So if you let n go to infinity here, this lower bound reproves this, recovers this theorem of Veropolis. I should give you something a bit more. And even if you don't care about the finite tree versions I've just been talking about, I think this is a rather nice consequence of this theorem. It doesn't just prove recover Veropolis' theorem, but it proves that there's a gap for the escape probability. So with the same little c appearing in this theorem, there exists no Cayley graph with escape probability between 0 and c. Okay, so if the escape probability is positive, by Veropolis' theorem, that means that the growth, and by this stuff I wrote here, that means that the growth is at least cubic. That means that this term in the minimum goes to infinity. So this minimum is just c. So the probability of escaping to distance n is at least c for large enough n. Yeah, so I didn't write, yeah, I apologies for not writing it down. It means that the random walk reaches the sphere of radius n without first returning to the identity. So it might then return to the identity, or it might then escape to infinity. We don't care. It just doesn't, it reaches that distance n without first returning to where it started. Right, yeah, yeah. Right, let's go over here. So, yeah, I'm going to change board order because otherwise this board keeps getting hidden behind the other. So the I've given similar talks on just this result, and there are a number of ingredients, but I want to focus on the growth in the Nilpotent stuff in this conference. So hopefully by showing you this Gromov's theorem and how that's relevant to the original Veropoulos' theorem, hopefully I've convinced you that it's not so surprising that such considerations are also important in proving this finite tree version. But I don't want to tell you how we get from results about growth to that finite tree version. What I do want to tell you is what we need to know about growth in order to prove it, and then tell you how we go about proving that. Okay. Now let me just remark. So I told you one consequence of Gromov's theorem is that every group has this degree of polynomial growth that there's growth is bounded above and below by. Well, in this group here, that's obvious, and the d is 0, because as n goes to infinity, the ball of radius n eventually has constant size. So that statement is completely trivial for this group. So just knowing that there's some integer d that bounds the asymptotic growth from above and below is not going to help with proving anything about this group here. So what we really need to do is, in some sense, understand how the growth behaves on a much finer scale. So here's another example which makes that hopefully quite clear. If you take the direct product of z squared and z mod nz, some large n, this to start with grows with degree 3. So again, the random walk has positive probability of reaching distance n without first returning. But then once it reaches n, the growth slows down and it starts growing with degree 2. Okay, so Gromov's theorem and the facts I put before will just tell you that this has asymptotic polynomial growth of degree 2, so it's recurrent, which is true. But in order to understand that you have positive probability of escaping to some given distance before you see the recurrence, you have to understand the growth on a finer scale. So here this grows like degree 3 and then degree 2. This grows like degree 3 and then like degree 0. And it might be tempting to wonder, having seen all this, whether you always start from some degree, which then just gets slower and slower and slower. Actually, that doesn't happen. There's this very nice example due to tau. Which shows that actually the degree of polynomial growth can go up as well as down. I'm going to look at the Heisenberg group of the integers G. And for my S, I'll take the following subset. So I'm just going to use a square brackets L notation to mean a set of integers between minus L and L. It's a bit non-standard, but we'll save a bit of time and space. So for my generating set, I'm going to take this kind of box in the Heisenberg group. And let's have a look at what the growth is like for this S. So S to the N is an exercise I'll let you think about it if you're so inclined. S to the N is not exactly the set I'm going to write down, but it's roughly like this. In a sense, I do not want to make precise. It looks roughly like this set. Okay, so here, if you start, S contains coordinates here between minus L and L. This is just the abelianization, so it really just does look like an abelian group. So it's not surprising you can get to, in n steps, you can get to NL, distance NL here and NL here. But here something different happens because you have so the group operation is somehow additive on this coordinate. So you can get to distance n, m just by taking an nth power here. But when you multiply two matrices from this group together, you multiply in this entry, you also see the multiple of this entry by this entry. And so that can give you elements as large as n squared, L squared. Okay, and in fact, you get some positive proportion of those, which is the sense in which this is roughly equal to this. Okay, so in particular, the size of n squared, s to the n, is asymptotically of the order, it's n cubed L squared m plus n to the fourth L to the fourth. So if you choose m to be much, much larger than L, this term dominates for small n. And so it looks to begin with as though the set is growing cubically. But in fact, hidden behind this massive m term here is this small but quartically growing n squared L to the fourth term. And so once n gets large enough, that's better. Okay. Did everybody hear everything so far? Good. Okay. Yeah, so this starts growing cubically, then grows quartically. And we can make it behave more interestingly. So let's say if we want to, we can quotient by some n here. So eventually you run out of room to grow in this direction, and then all you see is the growth here. So then it goes with degree 2. And if we wanted to, we could also then quotient by something here and here and make it go down to 1 and then 0. But hopefully you get the idea. So it can go up and down. And what Tao proved when he made this example is that the local slope, if I can call it that, is always like a polynomial of integer degree. And there are only finitely many changes of degree. And the largest degree you can see is bounded in terms of the first degree that you see. So there's some control on this, but it can go up and down, boundedly many times. No, good question. If you bound, that's actually in the first paper in this long series of papers Roman and I have, one of the first results we proved was that if you impose a bound on the size of S, then indeed it only decreases. Yeah, so this, you really do need to take this large M. This is important. Say again, sorry. Oh, you mean how big S has to be in order? I mean, basically, yeah. So it won't depend on the group. It'll depend on the degree. So all of the bounds in the things I'm going to talk about, I'll make this explicit when I write down general results. But the bounds in general depend on the degree that you witness at the first scale, and nothing else. And actually, it turns out that in order to prove our theorem about escape probabilities, we, hopefully it's already clear from the statement of Vertex-transitive theorem that somehow what we need to understand is what happens between degree 2 and 3. The precise statement we need in order to prove this is that, so I'll write, yeah, okay. What we need and what we prove is the following. If we basically prove that this phenomenon where you get the increase in degree, we need to prove that that can't happen if the first degree you see is 2. So we need to show that you can't actually, although you can jump from 3 to 4, you can't jump from 2 to 3. So if S to the n is at most epsilon times n to the 3 times the size of S, then where epsilon is some well, constant that will depend on D for the general result, but universal constant for this specific statement, then S to the M n size at most some constant times M squared times the size of S to the N. So if you grow a little bit smaller than cubically, then at some scale, then from then on you can grow at most quadratically. Okay, so that's what we need to prove in order to get it. Right now I'm running a bit short of time, so I might just say some stuff out loud that I was going to write down, so that I can then write down a general. I've had time to write down a general theorem for you. What I wanted to say is that, well, somehow I will write some stuff down. So this example here, we had a box, what I call a box. This LLM thing, this S here, S was a box inside the Heisenberg group of Z, which is in turn a lattice in the simply connected Nilpotent Lie group, Heisenberg group over R. And basically, in any lattice in a simply connected Nilpotent Lie group, you could construct examples like this. But you're constrained somewhat. So the first degree of growth you see in such a group has to be at least the dimension of the Nilpotent Lie group. So here we had degree 3 to start with. We had no hope of starting with anything smaller than that. And the largest degree you can hope to see is what's called the homogeneous dimension of that Nilpotent Lie group. Okay, so for the sake of time, I won't. If you know what that means, great. If you don't know, I'll tell you enough about it in just a second. You can understand. But in the case of the Heisenberg group, the homogeneous dimension is 4. Dimension is 3. Homogeneous dimension is 4. So we were able to start at 3 and jump to 4, but there was no way we were going to jump any higher than 4. And basically, the reason that this is true is because if you start with something, if you have a say you wanted to try and construct an analogous example that went from degree 2 to 3, to start with growth that's less than cubic, you would have to start in an Nilpotent Lie group whose dimension was less than 3. But the only simply connected Nilpotent Lie groups of dimension less than 3 are R and R squared to both abelian. And in an abelian group, the homogeneous dimension and the dimension coincide. So really, this fact really crucially depends on the fact that the only Nilpotent Lie groups of dimension 2 are abelian. Okay. So you can have analogous results for larger values of D here, and here, rather than if you have D, let's say if you put D plus 1 here, rather than D here, you have to put the homogeneous dimension, the largest possible homogeneous dimension of a Lie group, of a Nilpotent Lie group of dimension D. Okay, so I would have written that down if I had a bit more time. If you didn't follow it, don't worry too much. So now in the last few minutes, I want to that was some general stuff about Lie groups. It's not obvious how, okay, so I've just told you you can't construct an example like this in the Lie group. It's not obvious why that means you can't come up with some other example. And actually our theorem tells you that if you have polynomial growth at some scale, then you have a very refined approximation at all scales by Lie groups of bounded dimension. That is enough to show that that's enough then to use this fact that if the degree is less than 3, then you're basically abelian. Unfortunately, the statement of the theorem is quite long, so it might even take me 5 minutes to write it down. So suppose let's say for all, I actually really want to, state the theorem of we are green tau first, because that's really a crucial starting point. So they show that if for all d, there exists n0 depending only on d, such that if the size of SVN, some generator of a group, is at most n to the d times the size of S, for some n at least n0, then there exists H and gamma normal in G, such that H is contained in the ball of radius n. H is also a subgroup of gamma. Gamma mod H is nilpotent of Hirsch length of D, and the index of gamma in G is at most some constant depending only on D. So this is somehow a one-scale version of Gromov's theorem. Gromov's theorem, if you assume polynomial upper bound on the size of all balls of radius n, you know that the group is virtually nilpotent. Here, you just need a polynomial upper bound on the size of one ball of radius n. So this is somehow the entry point to proving things about growth where you only know something about small scales. And basically what we do is dramatically refine the conclusion of this theorem. Okay, so I'm really not going to have time to write down our results, unfortunately. What's the best thing to do? Okay, let me tell you some things we can refine about this theorem. And I'll highlight which ones are the most crucial for proving this. So, okay, so basically what we do is we prove that if you have, starting from this, let me tell you this. So the one thing we prove, that this K of D here that they have is ineffective. So there was no explicit bound on the index of gamma. What we're able to do is bound it by not only an explicit function of D, but the optimal value of D. So G of D is the maximum size of a finite subgroup of GL and Z. And to see that's optimal, you can just consider Z, so the D, that should be D, sorry. See that's optimal, we consider the semi-direct product Z to the D with some finite subgroup of GLDZ of maximum size. We also replace this Hirsch length O of D with exactly Hirsch length D on the nose. And that's what's crucial here, because somehow, so we also prove some we also prove that these balls of radius n, they don't just lie in this modulo H in an nilpotent group. We show that we can very precisely approximate these balls by, we show they're locally isomorphic mod H to Lie groups. And the dimension of the Lie group that we get at the beginning of this sequence is bounded by the Hurst length here. So this D, if you start with a 2 here, you get Hurst length 2 there, which then bounds the dimension of the Lie group you're using by 2. And then you can do what I explained here. I think that I should stop there. Thank you. Oh, someone has a question. Yeah. What's the question? Yeah, it's a good question. I don't know. I wouldn't be surprised if there were other gaps, but I have no strong reason to believe that there should. I don't know.